In this module, you will learn about Cartesian product of sets. Take a look at the pair of entries A and B, which are separated by a comma and are enclosed within the bracket. Such type of a pair is called an ordered pair, where A is the first element and B is the second element. If we change the order of A and B, we get a different ordered pair. In this case, B is the first element and A is the second element. The order in which the entries are written in an ordered pair is specific. Let us assume the value of A to be 4 and B to be -3. Then, this point denotes the ordered pair 4 minus 3. On changing the order of A and B and plotting -3, 4 on the coordinate plane, we see that both the points are in different quadrants and do not coincide. Hence, a pair of entries grouped in a particular order, which are separated by a comma and enclosed within brackets, is called an ordered pair. If two ordered pairs are equal, then their corresponding first elements and second elements are equal. If the ordered pair A-B is equal to the ordered pair 1-4, then it implies that A is equal to 1 and B is equal to 4. Let us now learn to find the Cartesian product of sets. Consider set X having the elements A, B, and M, and set Y having the elements F, C, D, and H. Let us find the product of sets X and Y. The product of sets means to pair the elements of sets together in a systematic manner. Let's see how we do this. Begin by forming an ordered pair from the first elements of each set. Progressively, change the second element of the ordered pair from set Y one by one till they get exhausted, keeping the first element of the ordered pair fixed. Next, take the second element of set X and again keep on changing the second element of the ordered pair from set Y till they get exhausted. Continue in this manner till all the elements of set X gets exhausted. This is the Cartesian product of sets X and Y and is symbolically denoted by X cross Y. Let us take one more example. Consider X to be the set of 4 different types of cards. Y denotes the set of all the numbers from 2 to 10, Jack, Queen, King, and Ace printed on the cards. The Cartesian product of two non-empty sets X and Y can be represented in the form of tabular cells or the point of intersection of perpendicular lines. In this case, the Cartesian product of sets X and Y will result in the set of all 52 playing cards as shown in the tabular form. From the above discussion, we can define the Cartesian product of two non-empty finite sets P and Q as the set of all ordered pairs of elements from them. In the set builder form, it is written as P cross Q is equal to the set of all ordered pairs PQ such that P belongs to set P and Q belongs to set Q. If either of the sets P or Q is a null set, then the Cartesian product will also be a null set. On the other hand, if one of the sets is infinite, then the resulting Cartesian product is also infinite. If there are m elements in set P and n elements in set Q, then the total number of elements in the Cartesian product of P and Q is equal to m multiplied by n. The product operation of sets can also be applied to a series of sets in sequence. If A1, A2, A3, up to An is a finite family of sets, then their Cartesian product is symbolically represented as the product of the given finite sets as shown. This is equal to the set of all ordered pairs consisting of the elements from each set. Hence, the Cartesian product of non-empty set A with itself 3 times is the set of all ordered triplets such that each element of the ordered pair is from set A. Now, consider R, the set of real numbers. The Cartesian product of R with R represents the coordinates of all the points in 2-dimensional space. And the Cartesian product of R with itself 3 times represents the coordinates of all the points in 3-dimensional space. The Cartesian product of 2 non-empty distinct sets is not commutative. Consider 2 sets A and B as shown. The Cartesian product of A and B is the set of ordered pairs 4, 3, 4, 1, 2, 3, and 2, 1. And the Cartesian product of B and A is the set of all ordered pairs 3, 4, 3, 2, 1, 4, and 1, 2. We notice that A cross B is not equal to B cross A. This implies the Cartesian product is not commutative. But if A and B are equal sets, then the Cartesian product of A and B is the same as the Cartesian product of B and A. Let us now discuss the distributive property. The Cartesian product of A with B union C is equal to the union of the Cartesian product of AB and AC. Let's verify this property. Consider sets A, B, and C as shown. Set B union C will have the elements 3, 4, 5, and 6. Let us evaluate the left-hand side of the property first. The Cartesian product of A with B union C is the set as shown. Now, let us find the Cartesian product of A and B, and A and C. Now, let's evaluate the right-hand side. The union of the Cartesian product of AB and AC is the set as shown. Hence, both the right-hand side and the left-hand side are sets consisting of the same ordered pairs. Hence, this property is verified. Similarly, the other 2 results of the distributive property can be verified. In this module, you will learn about relations. Rita is the sister of John. John is a student of Mr. Smith. This bus belongs to the school. In all these statements, one individual or object is related to another by some relationship. In the first statement, is the sister of is the relation. In the second statement, is a student of is the relation. and in the third statement, belongs to is the relation. A relation gives a connection or an association between objects, ideas, quantities, or individuals. Relations also exist between groups of objects, ideas, quantities, and individuals which form sets. Before proceeding further with relations, let's take a quick look at how we find the Cartesian product of sets. Let S be a set having 3 elements and D be a set having 2 elements. The Cartesian product of S and D can be obtained by pairing each element of set S with the elements of set D in a specific order. We see that the Cartesian product of S and D has 6 ordered pairs, which are as shown. Let's now come back to relations. Let X denote the set of collection of different subjects and Y denote the set of collection of topics. The possible combinations of the subjects and the topics are the set of ordered pairs that can be obtained by the Cartesian product of sets X and Y. The total number of such possible ordered pairs is 15. Let us now introduce a relation between the first and the second elements of the ordered pair such that the second element is a topic of the first element. That is, all ordered pairs XY such that Y is a topic of X, where X belongs to set X and Y belongs to set Y. This is the set builder representation of the relation R. In the roster form, we list all the ordered pairs that satisfy the formula given in the relation. It has 4 ordered pairs: mathematics sets, mathematics circles, biology cells, chemistry atoms. This relation can also be represented visually with the help of an arrow diagram as shown. Hence, we can describe a relation in different ways: list form or roster form, set builder form, and arrow diagram. Let us now define a relation. A relation from a non-empty set A to a non-empty set B can be defined as the subset of the Cartesian product of A with B, which is obtained by describing a relationship between the first element and the second element of the ordered pairs. The property that explains how the elements in each ordered pair are related is called the rule of relation or the formula of relation. Let us now find the range, domain, and codomain of the relation R. The set of the first coordinates of all the ordered pairs of a relation R is called the domain of R. In this case, the domain of R has 3 elements, namely mathematics, biology, and chemistry. Observe that the repeated elements are written only once. And the set of the second coordinate of all the ordered pairs of R is called the range of R. The range of R in this case has 4 elements, namely sets, atoms, cells, and circles. The second set is called the codomain. In this case, Y is the codomain of the relation R. From the above discussion, we observe that range is a subset of codomain. The total number of relations that can be defined from a set A to a set B is the number of possible subsets of A cross B. If the number of elements in set A is P and the number of elements in set B is Q, then the total number of ordered pairs in the Cartesian product of A and B is PQ, and the total number of relations from A to B is 2 raised to the power PQ. Let us find the possible number of relations that can be defined from set X to Y. The number of elements in set X is 3, and the number of elements in set Y is 5. This implies that the total number of elements in the Cartesian product of A and B is equal to 15. Hence, the total number of relations defined from A to B is equal to 2 raised to the power 15. In this module, you will learn about functions. A relationship between two sets of information is called a relation. In mathematical terms, a relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product of A and B. Let us consider an example. Let A and B be two sets as shown, and let R be a relation from set A to set B defined by the set of ordered pairs x, y, such that y is equal to x plus 1. It implies that R is a set having ordered pairs 1, 2, 2, 3, 3, 4, 4, 5, which is a subset of the Cartesian product of A and B. The domain of the relation R is A. The codomain of the relation is B. And the range of the relation is a set with the elements 2, 3, 4, and 5. Also notice that the range is always a subset of the codomain. Now observe the following statements. Let X be a set of books in a shop, and Y be the set of prices that correspond to each of the books in the shop. We have a correspondence between the books and their prices. Let N be the set of natural numbers and C be the set of cubes of all the natural numbers. We can assign each natural number to its cube, giving a correspondence between the two sets, N and C. Observe that in each of these examples, we have two sets, and a rule that assigns to every member of the first set a unique element of the second set. Function is a type of a relation that assigns to every member of one set a unique element of another set. Hence, we can say that every function is a relation, but every relation is not a function. Let's look at functions in a little more detail. Let A and B be two sets as shown. Let A and B be two sets as shown. Also let R be a relation from set A to set B, defined by the set of ordered pairs x, y, such that y is equal to x plus 1. This arrow diagram represents this relation. Observe that all the elements of set A have a correspondence with the elements of set B. Also, every element of set A has only one correspondence with the elements of set B. Such type of relations in which every element in the domain set has one and only one image in set B are called functions. Let's now define function mathematically. Let A and B be two non-empty sets. A function f from A to B is a rule that maps each member of set A with a unique member of set B. In other words, a relation R from a non-empty set A to another non-empty set B is said to be a function if its domain is set A and no two ordered pairs of R have the same first coordinates. For example, let F be the set as shown. The ordered pairs 3, 9 and 3, 11 belong to set F. Observe that both the ordered pairs have the same first coordinates. Hence, the given relation is not a function. Let us take one more example to understand it better. Let F be the set of ordered pairs x, x, such that x is a real number. In this relation, for all real numbers, there exists an image that is the same real number. Hence, the given relation is a function. We can thus conclude that f is a relation from set A to set B, and f is said to be a function from A to B. If for all x belonging to A, there exists a unique y belonging to B, such that the ordered pair x, y belongs to f. Let f be a function from set A to set B. Then, set A is known as the domain of the function, and set B is known as codomain of the function. If f is a function from A to B, and the ordered pair x, y belongs to set F, then y is called image of x under function f, and we denote this as f of x is equal to y. Also, x is known as the pre-image or inverse image of y. The ordered pairs 1, 2, 2, 3, 3, 4, and 4, 5 belong to f. F of 1 is equal to 2, which implies that 2 is the image of 1, or 1 is the pre-image or inverse image of 2. Similarly, for the other ordered pairs, we have the images and pre-images as shown. Let us now define the range of a function. If f is a function from A to B, then the set of all images of elements of set A is known as the range of function f. It is denoted by f of A. As you know, the range of a function is a subset to the codomain of the function. The range of f is the set having the elements 2, 3, 4, and 5. And f of A is a subset of B. In y is equal to f of x is called the independent variable, while y is known as the dependent variable. The dependent variable is also called the value of the function f at x. Let us consider a function f from A to R defined by 2x plus 1, where A is a set having the elements 1, 2, and minus 1. Let us find the ordered pairs satisfying function f. F of 1 is equal to 2 into 1 plus 1. This is equal to 3. f of 2 is equal to 2 into 2 plus 1. This is equal to 5. F of minus 1 is equal to 2 into minus 1 plus 1. This is equal to minus 1. This implies that the ordered pairs 1, 3, 2, 5 and minus 1, minus 1 are the elements of F. Let's now consider some more examples in which we are given arrow diagrams of some relations. Let's check which of them are functions. In these examples, 1 and 2 are functions because every element in set A has a unique correspondence in set B. However, 3 is not a function because one element in set A has no correspondence with any of the elements of set B. And also, 2, y, 2, z are the ordered pairs having the same first elements. 4 is also not a function because an element 2 in set A has correspondence with two elements y and z of set B. Or 2, y, 2, z are the ordered pairs having the same first elements. Every relation can be represented with the help of a graph. When a graph of a relation is drawn, we can use a test to determine whether it is a function. This test is known as the vertical line test. Let us consider the graphs of two relations. Draw a vertical line parallel to the y-axis such that it intersects the graph. If the vertical line intersects the graph at more than one place, it means that two ordered pairs have same first coordinates. Then we can conclude that it is not a function. In the first graph, the vertical line is intersecting the curve only at one point. Hence, it is the graph of a function. However, in the second graph, the vertical line is intersecting the graph at two different places. Hence, the given graph is a relation, but not a function. A function that has either the set of real numbers or one of its subsets as its range is called a real-valued function. Further, if the domain of the function is also either the set of real numbers or a subset of R, it is called a real function. Now, let us learn how to add two real functions, subtract one real function from another, multiply a real function by a real number, and multiply or divide one real function by another. Let's begin with the addition of two functions. If f and g are two real functions from x to r, the set of real numbers, such that x is a subset of r, then f plus g is also a function from x to r, defined as f plus g of a is equal to f of a plus g of a for all a belonging to set X. Let f and g be the sets as shown. F of 1 is equal to 2 and g of 1 is equal to 5. Then f plus g of 1 is equal to f of 1 plus g of 1, that is 2 plus 5. This implies that the ordered pair 1, 2 plus 5 belongs to set f plus g. Similarly, you can get 2 more ordered pairs. Hence, f plus g has 3 ordered pairs. (1, 7, 2, 9, and 3, 11). Now let us learn the subtraction of one real function from another. If f and g are two real functions from x to r, such that x is a subset of r, then f minus g is also a function defined from x to r by f minus g of a is equal to f of a minus g of a for all a belonging to set x. Again, let us consider sets f and g as shown. F minus g of 1 is equal to f of 1 minus g of 1, that is 2 minus 5. This implies the ordered pair 1, 2 minus 5 belongs to set f minus g. Similarly, you can get 2 more ordered pairs. Hence, f minus g has 3 ordered pairs. (1, minus 3, 2, minus 3, 3, minus 3). Next, let us learn the multiplication of a real function with a real number. Let f be a real function from x to r and k be a real number. Then, the product of k and f is a function from x to r defined by kf of a is equal to k multiplied by f of a for all a belonging to x. Let us again consider set f and k is equal to 2. If f of 1 is equal to 2, then 2 multiplied by f of 1 is equal to 2 multiplied by 2. This implies that the ordered pair 1, 2 multiplied by 2 belongs to a set 2f. Similarly, you can get 2 more ordered pairs. Hence, set 2f has 3 ordered pairs. (1, 4, 2, 6, and 3, 8). Let's now learn the multiplication of two real functions. The product of two real functions f and g from x to r, where x is a subset of r, is a function fg from x to r defined by fg of a is equal to f of a multiplied by g of a for all a belonging to set x. Consider sets f and g. F multiplied by g of 1 is equal to f of 1 multiplied by g of 1. This is equal to 2 multiplied by 5. This implies the ordered pair 1, 2 multiplied by 5 belongs to function f multiplied by g. Similarly, you can get 2 more ordered pairs. Hence, set f multiplied by g has 3 ordered pairs. 1, 10, 2, 18, and 3,28. Let us now learn how to find the quotient of two real functions. Let f and g be any two real functions from x to r, where x is a subset of r. Then we define f divided by g from x to r by f divided by g of a is equal to f of a divided by g of a, provided g of a is not equal to 0 for all a belongs to x. Consider sets f and g. F divided by g of 1 is equal to f of 1 divided by g of 1. This is equal to 2 divided by 5. This implies the ordered pair 1, 2 divided by 5 belongs to set f divided by g. Similarly, you can get two more ordered pairs. Hence, function f divided by g has three ordered pairs: 1, 2 divided by 5, 2, half, and 3, 4 divided by 7. In this module, you will learn about different types of functions and their graphs. The relation f from a set A to set B is said to be function if every element of set A has one and only one image in set B. In other words, a function f is a relation if no two ordered pairs in the relation have the same first element. A function that is a relation between two sets can be represented graphically because it is the set of ordered pairs and can be plotted on the Cartesian plane. The notation f from A to B means that f is a function from A to B, where A is called the domain of f and B is called the codomain of f. Given an element A from set A, there is a unique element B in set B that is related to A. The unique element B, to which f relates A, is denoted by f of A and is also called the value of f at A, or the image of A under f. The set of all the values of f of A taken together is called the range of f, or the image of A under f. Symbolically, the range of f is the set of all B such that B is equal to f of A for some A in A. In this case, the range of f is equal to the codomain of f. Let's now discuss different types of functions and their graphical representation. The first function we are going to discuss is the identity function. An identity function is a function f from set R to set R, such that f of x is equal to x for all x belonging to set R. An identity function is denoted by I with subscript R. Let A be the set having elements 1, 2, and 3. Then, the function f defined on A by f of x is equal to x is the set of ordered pairs 1, 1, 2, 2, and 3, 3. This is an identity function. Since for this, both the entries or the elements in the ordered pairs 1, 1, 2, 2, and 3, 3 are the same, the graph for this function will be a straight line passing through the origin. Each point on this line is at equal distance from the coordinate axis. This straight line makes an angle of 45 degrees with coordinate axis. Thus, the graph of a real function f from R to R, defined by f of x is equal to x for all x belonging to R, is as shown. Now, let's see how the graph of a linear function looks like. A function f from R to R is said to be a linear function if f of x is equal to ax plus b, where a is not equal to 0, a and b are real constants, and x is a real variable. Consider the linear function. F of x is equal to 3x plus 7 for all x belonging to the set of real numbers. Some ordered pairs satisfying the linear function are on plotting these points on the Cartesian plane and then joining them, we get the graph of the linear function f of x is equal to 3x plus 7 for all x belonging to R as shown. Let's now move on to the constant function. A function f from R to R is said to be a constant function if f of x is equal to c, a constant for all x belonging to R. Let f be a constant function from R to R, defined by f of x is equal to 4 for all x belonging to the set of real numbers. Some ordered pairs satisfying the linear function are. Observe here that in all the ordered pairs, the second element are the same. That is, the range has only one element, that is 4. In other words, if the range of a function is a singleton set, then it is a constant function. On plotting these points on the Cartesian plane and then joining them, we get the graph of the constant function f of x is equal to 4 for all x belonging to R as shown. Also from the graph, we can conclude that the graph of a constant function f of x is equal to c is always a straight line parallel to the x-axis, intersecting the y-axis at 0, c. Let's now proceed to the polynomial function. A function f from R to R is said to be a polynomial function if for all x in R, y is equal to f of x, which is equal to a0 plus a1x plus a2x square plus so on up to anx raised to the power of n, where n is a non-negative integer and a0, a1, a2 and so on up to an are real numbers. Some examples of polynomial functions are f of x is equal to x squared plus 5x plus 6 and f of x is equal to x cubed plus 4x plus 2. Note that in a polynomial function, the powers of the variables should be non-negative integers. For example, f of x is equal to square root of x plus 2 for all x belonging to R is not a polynomial function because in this case, the power of x is a rational number. Let us now consider the polynomial function f of x is equal to 3x squared plus 2x minus 3 for all x belonging to the set of real numbers. Some ordered pairs satisfying the polynomial function are. On plotting these points on the Cartesian plane and then joining them, we get the graph of the polynomial function f of x is equal to 3x squared plus 2x minus 3 for all x belonging to R as shown. Now, let's learn about the rational function. Let f of x and g of x be two polynomial functions. Then, f of x divided by g of x, where g of x is not equal to 0 and x belongs to R, is known as a rational function. Let us consider the function f of x is equal to 2x minus 5 divided by 3x minus 2, where x is not equal to 2 divided by 3. Some ordered pairs satisfying the given function are on plotting these points on the Cartesian plane and then joining them, we get the graph of the given rational function as shown. Now, proceeding to the modulus function. A function f from R to R defined by f of x is equal to mod x for all x belonging to the set of real numbers is known as a modulus function. If x is negative, then the value of the function is minus x. And if x is non-negative, then the value of function f is x. That is, f of x is equal to x if x is greater than or equal to 0, and minus x if x is less than 0. Some ordered pairs satisfying the modulus function are on plotting these points on the Cartesian plane and then joining them, we get the graph of modulus function f of x is equal to mod of x. The next function that we are going to discuss is the signum function. A function f from R to R defined by f of x is equal to mod x divided by x is called a signum function. That is, f of x is equal to 1 if x is greater than 0, 0 if x is equal to 0, and minus 1 if x is less than 0, for all x belonging to the set of real numbers. Some ordered pairs satisfying the signum function are on plotting these points on the Cartesian plane and then joining them, we get the graph of signum function f of x is equal to mod of x divided by x. The domain of a signum function is the set of real numbers, and the range is the set having the elements minus 1, 0, and 1. It is also written as sin x. Now, let's discuss the last function, called the greatest integer function. A function f from R to R, defined by f of x, is equal to the greatest integer, less than or equal to x for all x belonging to the set of real numbers. Such a function is called the greatest integer function. From the definition, its value is equal to minus 1 for x is greater than or equal to minus 1 and less than 0. The value is 0 if x is greater than or equal to 0 or less than 1. 1 if x is greater than or equal to 1 and less than 2. 2 if x is greater than or equal to 2 and less than 3. This implies f of 2.5 is equal to 2, and f of 1.2 is equal to 1, and so on. Hence, the graph of the greatest integer function is as shown.